Right. Good afternoon, everyone again. So I have prepared a few slides to introduce the topic and mainly what I'm doing, and see if we can start any conversation. So first of all, my research interest is about vibration isolation. And currently, I'm learning and searching new materials to mitigate vibration to structures, in particular to buildings, but also bridges. And we are exploring together with the team other applications. So the challenge that we want to tackle is the increase of population living in cities. You probably have heard about the estimation from UN. They estimated that by 2050, more than 70% of the world population will be living in cities. So we have rapid urbanization, environmental threats, but also natural disasters that will expose structures and infrastructure to new challenges. This is exacerbated by the exposure to noise and vibrations. For example, due to vicinity to underground lines and then train stations, traffic noise, but also earthquakes. So the aim then for designers and planners is to make cities more resilient against the impact of natural hazards, disasters, and work around enhancing and improving the structures and infrastructures. Another challenge combined to this is the rubber waste. Tire manufacturing is the largest contributor to rubber waste. I think, if I remember correctly, around in 2018, about 3 million tons of tires were removed from service in Europe alone, and until 2006, those waste were stored in landfills, but then in 2006 this was banned. So the immediate solution would be try to reuse this material. How do we mitigate vibrations then? So the most widely used technology is isolation. Isolation is used in earthquake-prone areas, for example, in San Francisco, but also in areas like also in London for structures or train stations, buildings close by the railways, or concert hall, for example, the Glasgow Royal Concert Hall. So how does it work? It consists of interposing a layer of rubber and steel together that, in a sense, decouple the superstructure from the foundation. So it's a very, very simple concept. I try to simplify as much as I can. So this pad is made of rubber and steel. That makes the system quite heavy. It needs to be bespoke to be designed specifically for that application. It requires special manpower. And the steel is quite essential because of the stability of the system. There has been a lot of studies try to remove steel and replace it with fiber-reinforced materials. But this fibers materials is very sensitive to alignment, it's very sensitive to preloading history. So essentially, although many studies, I think it's about 10, 12 years, it never went to real applications. Those devices are also used in bridges and are used for allow natural movements caused by thermal expansion or contraction, fatigue, and creep. So they are used in structures like buildings, but also in bridges. And similarly, they are used in other applications, like for sensitive machinery. Obviously, they are scaled down. So what we wanted to do is to explore the use of recycled rubber combined with a thin layer of graphene to mitigate ground-borne induced vibrations. Graphene is you probably know more than me, because my background is definitely not material or metamaterials, but graphene is one atom thick layer of carbon, so it's a very strong, and we have tried to coat natural and recycled rubber with the layer of graphene to see whether this could replace the use of steel. What are the advantages? Making those devices lighter, making those devices easy to manufacture, more accessible, but also sustainable, avoiding using recycled rubber essentially. In terms of applications, as I said, is for structural infrastructure in earthquake-prone areas, but also for train-induced vibration, for mitigating those kind of vibrations, but also for sensitive machinery. And actually, we have been talking with industry from various sectors, from railway, recycle rubber industry, gas and oil industry, and we have received a very positive feedback, and about 70% of those industry they suggest that there was a real and urgent need of addressing this key point of proposing sustainable solution for vibration mitigation. So that was quite a good start for us, and it was an indicator that actually we were going into the right direction. We have also presented this idea to the new European Bauhaus as a sustainable and innovative solution throughout the use of recycled rubber, low maintenance solution to mitigate vibration in buildings. Initially, so our initial prototype, and actually the initial idea, has been proposed at the Create the Future 2020, which is an international competition, and we have been selected among the top 100 entries worldwide. So it attracted a lot of interest. As part of the initial research and investigation, we fabricated a few prototypes that we tested with the facilities, small facilities that we have at the University of Exeter. So we performed dynamic tests on those devices. We are at the moment looking at expanding the facilities and making larger size of these devices and test them. But anyway, the initial tests show us that the deposition of layers of graphene on recycled rubber pads lead to better mechanical properties as compared to pure rubber. And what we wanted to do, we wanted to control the damping, possibly increasing the damping and increasing the vertical stiffness of the composite. And we were quite, the initial results were very promising. So that is what I'm working on at the moment. You probably have, there are a few topics that I would like to bring up to the conversation. The first one is about the dynamic properties of materials, metamaterials, how we can control and improve and enhance in a sustainable way. The second aspect would be industry's challenges. We have, as I said, we have engaged with a number of industries, and a net zero challenge is the common aspects, but there are others definitely. Another aspect is about the testing facilities. So how we testing these materials, prototyping, testing, using innovative techniques maybe, and scaling up. So it's a matter of bringing the material or the proposed solution from the lab to real applications, and I guess this is the transition and the biggest challenge. So those are, I guess, the 4 points that I would like to start with. If anyone want to start this conversation, but I'm happy to keep open as much as possible this conversation.